Deep space whispers secrets we have yet to understand. These are the unexplained signals from neutron stars, the universe's densest objects. They are stellar corpses, the collapsed cores of dead suns, where gravity is so intense a single teaspoon of their material would weigh billions of tons. Their magnetic fields could strip the data from every credit card on Earth from halfway across the galaxy. And from these extreme realms, we catch bizarre transmissions, radio bursts that outshine galaxies, rhythmic pulses that suddenly vanish, and patterns that defy all known physics. By the end of this journey, you will have explored 25 of the most baffling cosmic enigmas ever detected. Why does one star seem to switch off for weeks at a time? What could cause a signal so powerful it was once mistaken for an alien greeting? The universe is sending us a coded message from the edge of reality. Are you ready to listen? In 1977, a radio telescope at Ohio State University picked up a signal so powerful and so strange that the astronomer who found it circled it on the printout and simply wrote, "Wow." That legendary burst, lasting 72 seconds, has fueled debates about extraterrestrial intelligence for decades. But it has a lesser-known cosmic cousin, one that points its mystery not at empty space but directly at the corpse of a star. This is our first unexplained signal. It came from a region of space dominated by a neutron star, a specific known celestial object. Discovered in 2007 by the Parkes Radio Telescope in Australia, the signal was a single, brilliant burst of radio waves. It lasted for about 5 milliseconds. In the blink of an eye, this burst released more energy than our sun does in 300,000 years. The sheer, staggering intensity was the first clue that something extraordinary had happened, but the real anomaly was its location. This immense flash of energy did not come from the chaotic depths of deep space. It appeared to originate from the vicinity of a magnetar, a type of neutron star with a magnetic field 1,000 trillion times stronger than Earth. Think of a lighthouse, the most powerful lighthouse in the universe, and then imagine a flashbulb going off right beside it that outshines the lighthouse beam by a factor of millions. That is what this was. The initial theories scrambled to explain it. Could it have been a starquake on the magnetar's surface, a catastrophic snapping of its crust under unimaginable magnetic stress? Perhaps it was the explosive annihilation of an asteroid that wandered too close, vaporized in an instant, yet the energy scales did not quite match. The signal was too clean, too isolated. This led some to more speculative ideas. What if it was a directed energy burst, a natural but focused beam from the neutron star's poles, pointed right at us by cosmic chance? Or, given the ghost of the wow signal, could it be something else entirely, a beacon? A pulse from a civilization that had built their transmitter around, or even from the power of a neutron star? The theories range from the rigorously physical to the profoundly speculative, and decades later, not a single one has been proven. We are left with a printout of our own, a spike on a graph from a known place, asking a question we still cannot answer. What in the heart of a dead star can create a whisper that screams across the galaxy? The wow signal left a tantalizing question hanging in the void, but the Lorimer burst provided a terrifying answer. It proved we were not just hearing whispers, we were being shouted at by the cosmos itself. This is our second unexplained signal. The story begins not with a live observation, but in the quiet archives of data. In 2007, astronomer Duncan Lorimer and his student were sifting through old recordings from the Parkes Radio Telescope in Australia, the same dish that would later find that first magnetar burst. They were looking for distant pulsars, the steady, ticking neutron stars, but buried in the noise from a single observation in 2001, they found something that should not have been there. A spike, a radio scream that lasted 5 milliseconds and then vanished forever. It was not a mistake, not an instrument glitch, not a passing satellite. The signal was so bright it saturated the telescope's receivers, and its most shocking feature was its dispersion. Radio waves traveling through the sparse gas of intergalactic space get slowed down, with lower frequencies arriving slightly later than higher ones. The amount of this delay tells you how much material the signal has traveled through, and therefore how far it has come. The dispersion of the Lorimer burst was immense. It placed its origin not within our Milky Way, but far beyond, in the distant, empty darkness between galaxies. That single fact made the energy calculation staggering. In those 5 milliseconds, this object released as much energy as our Sun does over 30 years. Picture the total solar output for 3 decades, the light and heat that sustains our entire planet, compressed into a flash shorter than a camera's shutter click. The astronomical community met this claim with deep skepticism. Could a single, unrepeatable event from archival data really be trusted? Perhaps it was a local artifact, a glitch from an oven microwave on the observatory grounds. The hunt was on to find another. For years, the Lorimer burst stood alone, a cosmic unicorn that many believed was a mirage. Then, one by one, others began to appear. New telescopes, more sensitive equipment, and dedicated surveys started catching these flashes in real time. They were given a name, fast radio bursts, and the Lorimer burst was retroactively crowned the first of its kind. The confirmation was a revolution. It meant the universe was filled with these catastrophic, ephemeral events, and the prime suspect for creating many of them. Magnetars, those same neutron stars with unimaginable magnetic fields. The theory suggests a magnetar might experience a starquake, a sudden rearrangement of its crust under magnetic strain so severe it cracks like a planet-sized neutronium egg, releasing a tsunami of energy as a radio blast. The Lorimer burst opened a window into a universe of violent, hidden transients, proving that sometimes the most profound discoveries are not found by looking up, but by looking back. The Lorimer burst was a singular scream in the dark, but what if the cosmos decided to start talking? That is exactly what happened with our third unexplained signal. Astronomers had settled into a grim understanding, believing fast radio bursts were one-off catastrophes, the final death cries of objects being destroyed. Then, in 2016, everything changed. The Arecibo radio telescope in Puerto Rico was monitoring a source known as FRB 121102, a burst first detected in 2012. To everyone's astonishment, it burst again and then again. Over time, it has flared up hundreds of times, an erratic, chatty beacon in the void. This was not a cosmic explosion. This was a source with a heartbeat, and it single-handedly rewrote the rulebook. The first major clue to its nature came from its address. Using the world's most powerful radio telescopes, scientists managed to pinpoint its home not to a majestic spiral galaxy like our Milky Way, but to a tiny, faint dwarf galaxy over 3 billion light-years away. This small, messy galaxy was forming stars at a furious rate, a nursery for massive, short-lived stars that die young and leave behind neutron stars. And right at the location of the repeating bursts, there was a faint, steady radio glow, a persistent radio source. This was the equivalent of finding a constantly smoldering campfire at the exact spot where sporadic fireworks keep going off. The repetition immediately ruled out the most dramatic one-time events, like 2 neutron stars colliding in a final, fatal embrace. You cannot have that cataclysm happen twice. So what, then, could power such a resilient cosmic repeater? One compelling theory involves a neutron star in a deadly dance. Imagine a pulsar, a spinning magnetized neutron star, in a tight orbit around a supermassive black hole or perhaps a massive companion star. As it swings through its orbit, periodic gravitational stresses or interactions with a surrounding disk of material could trigger regular outbursts like a clockwork volcano. The leading theory, however, points to a supremely active young magnetar. This neutron star, born from a recent supernova in that star-forming galaxy, could be surrounded by a thick, turbulent nebula of debris from its explosive birth. When the magnetar has a starquake, the resulting blast wave slams into this surrounding nebula, creating the radio burst we see. The persistent radio source could be the glow of that very nebula, constantly energized by the magnetar's fierce wind. This model paints a picture of a chaotic, energetic nursery, a newborn stellar corpse throwing tantrums inside its own dusty cradle. The repeating bursts of FRB 121102 transform these signals from cosmic mysteries into potential cosmic laboratories. We are no longer just listening for random bangs in the night. We are starting to observe a personality, a source with a history and an environment we can study. It begs a haunting question: if one source can repeat, how many others are simply waiting for us to listen again? Repeaters like FRB 121102 taught us that some cosmic voices have more to say, but what if the loudest conversation of all was happening right in our own galactic backyard and we could barely hear it? This is our fourth unexplained signal, the galactic center burster. For decades, astronomers have known about a strange source near the very heart of the Milky Way. It erupts not in radio waves, but in powerful flares of X-rays and sometimes radio emissions, lighting up for brief, unpredictable periods before fading back into obscurity. Its outbursts are not on a neat schedule. They are erratic, sometimes arriving in quick succession, other times remaining silent for months or even years. This irregular cadence makes it maddeningly difficult to study, a cosmic firefly blinking on its own inscrutable timetable. The challenge of understanding it is compounded by its location. To observe the galactic center, our telescopes must peer through 26,000 light-years of space crowded with interstellar dust and gas. This material acts like a dense cosmic fog, scattering and absorbing the very light we are trying to see. It is like trying to spot a specific blinking light on a distant shore through a raging blizzard. Only the most penetrating forms of energy, like X-rays and certain radio wavelengths, can punch through this murk, and even then, the signal arrives distorted and faint. So what could this hidden burster be? The leading theory paints a dramatic picture of celestial cannibalism. Imagine a binary system, a neutron star locked in a gravitational embrace with a more normal, sun-like companion star. But this is no peaceful orbit. The neutron star's immense gravity acts as a cosmic vampire, relentlessly pulling streams of gas away from its companion. This stolen material spirals down toward the neutron star, forming a superheated disk of plasma called an accretion disk. As this material builds up, it can become unstable, suddenly crashing onto the neutron star's surface in a thermonuclear avalanche that we see as a brilliant X-ray flare. The irregular timing could be due to the messy, clumpy nature of the accretion flow. But there is another, even more exotic possibility. What if the burster is a lone magnetar, a neutron star with a magnetic field so titanic it is literally twisted? This twist could cause the star's magnetic axis to wobble or precess over time. Think of a spinning top that slowly circles as it rotates. If the beam of radiation from this magnetar's pole only points directly at Earth during a certain part of that wobble, we would see bursts of activity separated by long, silent gaps. This would make its eruptions not random, but on a grand, slow cycle we have not yet fully mapped. Whether it is a starving neutron star feeding on its neighbor or a wobbling magnetic giant, the galactic center burster represents a persistent puzzle in our own cosmic city center, a reminder that some of the most violent and mysterious conversations in the universe are happening just down the street, whispered through a veil of dust. The heart of our galaxy whispers through a veil of dust, but one magnetar decided to send a message so clear it could not be ignored. This is our fifth unexplained signal, the cosmic heartbeat of SGR 1935 plus 2154. For years, the connection between magnetars and the mysterious fast radio bursts was a compelling theory, a strong suspicion based on energy and location. Then, in April 2020, suspicion became certainty. This particular magnetar, located about 30,000 light-years away in our own Milky Way, did something unprecedented. It erupted in a furious storm of high-energy radiation, and nestled within that storm was a brilliant millisecond flash of radio waves, a bona fide fast radio burst coming from a known, identified object. The galactic mystery was solved, at least for one type of these bursts, but the magnetar was not finished. In the tumultuous aftermath of that violent radio scream, something else persisted. A steady, rhythmic pulse of X-rays began to beat from the star, like a cosmic metronome ticking once every 3.8 seconds. This was the heartbeat. It continued for days, long after the initial chaos subsided. That persistent rhythm is a profound clue. It tells us that despite the cataclysm that just occurred, the magnetar itself remained fundamentally intact. Its engine, the rapid spin powered by its incredible density, kept turning. The heartbeat is the signature of that spin, a lighthouse beam of X-rays sweeping past Earth with every rotation. So what caused the explosion? The leading culprit is a starquake. Picture the magnetar's surface, a crust of iron nuclei forged into a crystalline lattice 10 billion times stronger than steel. Yet it is trapped in a magnetic prison 1,000 trillion times stronger than Earth's field. This creates unimaginable stress. The magnetic field lines, anchored in the star's interior and stretching out into space, can twist and writhe like tangled rubber bands. Eventually, the tension becomes too great. Something has to give. The crust itself cracks. In a fraction of a second, a vast tectonic plate on this stellar corpse shifts, releasing pent-up energy equivalent to a magnitude 32 earthquake. This sudden snap reconfigures the magnetic field lines, and as they reconnect and reorder, they unleash a torrent of radiation, the X-ray storm, and the fleeting, focused beam of the radio burst. The fact that the steady heartbeat pulses through this violence suggests the quake was a surface event, a rearrangement of the star's outer shell and its magnetic crown, not a disruption of its deep, spinning core. We are essentially listening to the star's vital signs as it recovers from a seismic trauma, its pulse steady even as its surface fractures. This single event transformed magnetars from suspects into confirmed perpetrators for some fast radio bursts, giving us a front-row seat to the most extreme geology in the universe, where mountains are made of nuclear material and quakes shine brighter than galaxies. A star's heartbeat can signal its health, but what happens when the beat slows to a crawl, defying every known rhythm of the cosmos? This is our sixth unexplained signal, the ultra-long period radio source known as GPMJ 1839-10. Its discovery shattered a fundamental rule. For over half a century, we understood neutron stars as nature's most precise metronomes, spinning anywhere from hundreds of times per second to once every few seconds. Their rapid pulses are a product of their birth, the conservation of a dying star's angular momentum crushed into an object the size of a city. Then along came this object, broadcasting a bright, clear radio pulse not every second but once every 22 minutes. To understand how bizarre this is, picture a familiar lighthouse. A typical pulsar is like a lighthouse beacon spinning so fast it appears as a constant blur of light, its beam sweeping past us hundreds or thousands of times a second. GPMJ 1839-10, by contrast, is a lighthouse that completes a single, languid rotation only once every 22 minutes. You could brew a cup of tea, read a few pages of a book, and still be waiting for the next flash. This glacial pace should be impossible for a classic neutron star. Theory states that if a neutron star spins this slowly, its magnetic engine should essentially shut off. The mechanism that powers its brilliant radio beams, which relies on a dynamo created by its swift rotation, would sputter and die, yet this source is not dead. It pulses brightly and reliably, archive data showing it has been doing so for at least 33 years. So what on earth, or rather, what in the heavens could it be? Astronomers are staring at an object that exists in a theoretical blind spot. One radical idea is that it is an ultra-long period magnetar, a neutron star with a magnetic field so incredibly strong it can somehow power radio emission even at this snail-like spin, like a battery with a charge that lasts for eons. Another possibility is that it is not a neutron star at all, but a white dwarf pulsar. White dwarfs are the Earth-sized embers of lower mass stars, and while some are known to pulse, none have ever been observed with such powerful, coherent radio beams. This would be an entirely new beast, a hybrid object that challenges the clean boundary between two classes of stellar corps. The implications ripple through astrophysics. If this is a neutron star, our models of magnetic field decay are profoundly wrong, and these magnetic giants can remain active far longer than we dreamed. If it is a white dwarf, it means these common stars can harbor magnetic engines violent enough to mimic their denser cousins. This one slow, patient pulse is a wrench thrown into the gears of stellar evolution, forcing us to reconsider what is possible in the final chapters of a star's life. It whispers that our catalogue of cosmic objects is still incomplete, and that the night sky holds retirees that refuse to fade quietly into the dark. The slow, patient pulse of a white dwarf candidate is a cosmic paradox, but sometimes a neutron star does not whisper a puzzle, it roars. This is our seventh unexplained signal. The Dragon radio burst from the magnetar SGR 1935 plus 2154. You have already met this star as the source of a galactic-fast radio burst and a steady X-ray heartbeat. But in October 2022, it produced something even more intricate and terrifying. Astronomers call it the Dragon, not for its mythical nature, but for the shape of its signal on their instruments. A main burst with a long, flickering tail of smaller pulses that resembled a dragon's fiery breath across their screens. This was not a simple flash, it was a storm within a storm. The event was captured across the electromagnetic spectrum, a crucial detail. As the Dragon unleashed its fury in radio waves, space-based telescopes simultaneously recorded a powerful flare of X-rays from the same spot. This multi-wavelength detection is like hearing a thunderclap and seeing the lightning bolt at the exact same instant, confirming the source and linking the radio chaos directly to the magnetar's violent physical processes. The real mystery, however, was in the fine print. The main radio burst was not a clean spike. Inside it, astronomers found a series of subbursts, smaller pulses that drifted downward in frequency over mere milliseconds. Imagine striking a bell and hearing not a single pure note, but a rapid cascade of tones sliding down a musical scale in the blink of an eye. This drifting structure is a fingerprint of a highly dynamic magnetized environment. One leading theory points to plasma instabilities within the magnetar's crushing magnetosphere. Picture the space around the star not as empty void, but as a seething ocean of charged particles trapped by magnetic fields. A sudden starquake could send shockwaves through this ocean, creating turbulent whirlpools of plasma. As these whirlpools form and collapse, they could emit radio waves at specific frequencies that quickly change, creating the drifting sub-pulses we see. Another compelling idea involves magnetic reconnection. The magnetar's field lines are under unimaginable stress, like rubber bands stretched to their breaking point. During a catastrophic event, these lines can snap and violently reconnect in a new configuration. This process is like a cosmic short circuit, releasing enormous energy in a burst of radiation and accelerating particles to near light speeds. The complex, flickering structure of the Dragon could be the signature of multiple reconnection events happening in rapid, cascading succession across the star's magnetic crown. Visually, you would see brilliant arcs of magnetic energy breaking and fusing like celestial lightning across the neutron star's surface, each snap unleashing a torrent of radio waves. The Dragon burst tells us that these cosmic explosions are not simple. They are textured, layered events offering a detailed look into the chaotic physics of a magnetic field so powerful it twists the very fabric of space around it. It is a reminder that when we listen closely to a star's scream, we can hear the complex machinery of its destruction. The dragon's roar showed us the surface chaos of a magnetar, but what if the strangest disruptions happen deep within the star's hidden heart? Our eighth unexplained signal takes us inside the neutron star itself to a phenomenon known as a glitch. The Vela pulsar, a cosmic lighthouse in our galactic neighborhood, spins 11 times every single second with a precision that rivals our best atomic clocks. But in 2010, the Fermi Gamma Ray Space Telescope caught it in the act of stumbling. For a fraction of a second, the star's rotation suddenly sped up, a tiny but definitive hiccup in its flawless rhythm. This is a glitch, and while not unheard of, the event was accompanied by something utterly new. The very shape of its gamma-ray pulse, the bright flash we see with each rotation, changed dramatically and then never returned to normal. To understand why this is so bizarre, we need to picture the interior of a neutron star. Think of it as a cosmic onion with layers of unimaginable states of matter. The outer crust is a rigid lattice of atomic nuclei. Beneath that, pressures become so intense that the core may contain exotic soups of free quarks or hyperons. Between the solid crust and the strange core lies a sea of superfluid neutrons. This superfluid has no viscosity, it flows without any friction at all. Normally, this superfluid rotates by forming tiny whirlpools called vortices. These vortices are pinned to the solid crust above, forcing both layers to spin in lockstep. The leading theory for a typical glitch is a starquake or a sudden unpinning of billions of these vortices. Imagine the crust under immense strain cracking like planetary-scale ice. Or picture those microscopic whirlpools all breaking free at once, transferring a massive amount of rotational energy from the frictionless fluid to the solid crust in an instant, giving the star's spin a sudden kick. This would cause a spin-up, which is exactly what was observed, but the Vela glitch did something more. The permanent change in its gamma-ray pulse profile is the real mystery. That pulse shape is our map of the star's emission zones, the bright hotspots at its magnetic poles where beams of radiation are launched into space. Altering that pulse shape means our map of the star's surface has been fundamentally redrawn. It suggests the glitch was not just a transfer of spin energy, it was a global event that reconfigured the star's very anatomy. The quake or vortex avalanche must have been so profound that it shifted the magnetic poles themselves, or permanently changed the geometry of the regions where the gamma rays are born. One radical interpretation is that the entire magnetic field, which is thought to be frozen into the superfluid core, underwent a sudden and catastrophic reorganization. It would be as if Earth's magnetic poles not only jumped locations, but the entire planetary magnetic field snapped into a new, stable configuration in a matter of seconds. The Vela glitch gives us a fleeting glimpse into the dynamic, violent life churning inside a neutron star, proving that even the most precise clocks in the universe can have their gears violently rearranged. A star's heartbeat can be stolen, but sometimes the entire voice vanishes for weeks on end. This is our ninth unexplained signal, the pulsar that switches itself off, PSRB 1931+24. Discovered in 2005, this neutron star exhibits a pattern so bizarre it seems almost artificial. For roughly 35 days, it pulses with perfect regularity, its radio beacon sweeping past Earth once every 1.6 seconds. Then, without warning, it goes completely silent. Its radio emissions drop by a factor of 99%, as if someone simply threw a cosmic switch. This radio blackout lasts for another 35 days before the pulsar flickers back to life, resuming its precise ticking as if nothing happened. This 35-day on, 35-day off cycle is staggeringly consistent, a metronome that controls not just the beat but the volume knob of the universe. The sheer precision of this pattern immediately captured imaginations and ignited wild speculation. Could this be evidence of some vast orbiting structure? The idea was sensational but not without precedent. Years earlier, the strange dimming of a distant star named KIC 8462852, Tabby's star, had led to fanciful theories of alien megastructures, vast swarms of solar collectors built by an advanced civilization. While that was later explained by dust, the pulsar's clean, periodic silence invited similar, if more cautious, comparisons. Could a planet or a swarm of asteroids be passing in front of the pulsar every 70 days, blocking its beam? The problem is physics. A solid object large enough to fully block a pulsar's beam would be utterly shredded by the star's ferocious gravity and radiation. Instead, astronomers look to more natural, yet still extraordinary, explanations rooted in the star's own environment. One leading theory involves a precessing debris disk. Imagine the pulsar is surrounded by a vast, clumpy ring of material, remnants from the supernova that birthed it or from a devoured companion. This disk is tilted and wobbles or precesses like a spinning coin slowing down. Every 70 days, this wobble brings a thick portion of the disk directly between the pulsar's pole and Earth, its dense plasma absorbing or scattering the radio waves into silence. Visually, you would see a brilliant lighthouse beam periodically sweeping behind a slow-moving, opaque cosmic curtain. Another compelling idea points inward to the star itself. Perhaps the pulsar's magnetic axis is slowly precessing independently of its rotation. The beam from its magnetic pole, the source of the radio emission, might only point directly at Earth during one half of this slow wobble, spending the other half aimed uselessly into empty space. This would make the pulsar not a clock that stops, but a lighthouse we only see during half of its grand, slow sweep. Both theories challenge our standard models of pulsar magnetospheres, which typically depict stable, unwavering beacons. PSRB 1931+24 suggests that some neutron stars live in messy, dynamic relationships with their surroundings, their clean signals periodically drowned out by the cosmic weather they themselves create. It is a reminder that silence can be as telling as a scream, and that a perfectly timed absence might be the universe's most intriguing signal. A pulsar's silence can be a perfect cosmic clock, but sometimes the signals we chase are not cosmic at all. Our 10th unexplained signal introduces the Puritans, the ghostly imposters that haunted astronomers for years. These were bursts of radio waves that looked, for all the world, like the fast radio bursts arriving from deep space. They had the right dispersion, the right brief duration, the right everything. Yet they all shared one peculiar trait. They were only ever detected during daytime observations at the Parkes Radio Telescope in Australia. This was a glaring clue, a footprint left at the scene of the crime. The universe does not keep business hours. The mystery deepened until a team of researchers decided to investigate the local environment with the diligence of cosmic detectives. They discovered that if a staff member at the observatory opened the door of a microwave oven before the timer had finished, the device would emit a brief, wide-frequency radio pulse. That pulse would then bounce off the observatory's metal structures and be picked up by the ultra-sensitive telescope, mimicking the signature of a signal that had traveled millions of light years. The visual is almost comical, a scientist heating up their lunch and, in a moment of hunger-driven impatience, accidentally generating data that sent other scientists on a wild goose chase across the cosmos. This discovery was not a failure of science, but a triumph of its process. It underscored the immense challenge of distinguishing a whisper from the edge of the universe from the mundane electronic hum of our own world. The Puritan episode led to a major overhaul of observation protocols. Radio telescopes now employ sophisticated filters and monitoring systems to identify and eliminate local radio frequency interference, from passing satellites to ground-based radar and, yes, even rogue kitchen appliances. It made the hunt for true cosmic signals cleaner and more reliable. This lesson in humility also casts a shadow of doubt on past anomalies. There are neutron star signals in old archives, odd bursts and patterns that were once dismissed as potential peritons or other interference. Now, with better tools and a more skeptical eye, astronomers are revisiting that data, wondering if a few of those discarded signals might have been cosmic treasures all along, hidden in plain sight amidst the noise of our own making. It is a reminder that the greatest obstacle to hearing the universe is sometimes the sound of our own civilization. Our own technology can mimic cosmic whispers, but a true stellar voice fading to silence is a different kind of mystery. This is our 11th unexplained signal, the lighthouse that is slowly going dark. Astronomers have monitored a pulsar known as PSRB 1508+55 for decades, and they have witnessed something deeply unsettling. Its radio beam is not just fluctuating, it is steadily, inexorably dimming. The star itself continues to spin, its rotation gradually slowing as expected, but the power of its radio shout is draining away. This is bizarre because a pulsar's spin and its radio emission are driven by two different engines. The spin slows as the star loses rotational energy, but the brilliant radio beam is powered by its monstrous magnetic field accelerating particles near the poles. One engine can idle while the other fails, so what could cause this specific failure? One possibility is a slow precession of the star's magnetic axis. Think of a lighthouse whose rotating light is mounted on a platform that is itself tilting on a centuries-long cycle. We are watching from a fixed spot on the shore. For decades, the beam has swept directly over us, brilliant and clear. But now, that grand, slow tilt is gradually pointing the beam away, so each pass grows fainter until one day it will miss us entirely, leaving the lighthouse shining brightly for some other part of the cosmic ocean. Another, more profound theory suggests the magnetic field itself is decaying at an unprecedented rate. A pulsar's magnetic field is its voice box, and if that field weakens, the particle acceleration that creates the radio beam becomes less efficient, like a speaker with a dying battery. The star could be entering a theorized but never seen Death Valley phase, a final quiet period where its magnetic engine sputters out long before its spin finally ceases. Visually, you would see the fiery auroras at its magnetic poles, those brilliant storms of radiation growing dimmer and more diffuse over centuries. The eventual silence of a pulsar tells us that these cosmic clocks do not just wind down, they can lose their voice. It forces us to ask what the end of a neutron star's active life looks like, not with a bang but with a fading whisper. This slow dimming is a eulogy written in real time, a reminder that even the most persistent signals in the universe are, on a long enough timeline, only temporary. A fading whisper is one fate for a neutron star, but another chooses a far more violent path to silence. This is our 12th unexplained signal, the cataclysmic outburst of an anomalous X-ray pulsar. These objects are a peculiar class of neutron stars that spend most of their lives in a quiet, steady state, glowing faintly in X-rays with a slow, regular pulse. They are not powered by feeding on a companion star, nor by rapid rotation like typical pulsars. Their steady light is a quiet hum, a mystery in itself, thought to be generated by the gradual decay of their unimaginably strong magnetic fields, a slow leak of pent-up energy. But every few decades, one of these sleeping giants awakens in fury. In 2003, an anomalous X-ray pulsar known as XTJ 1810-197 did just that. Over a matter of hours, its X-ray brightness did not just double or triple, it exploded by a factor of 100. Imagine a single, dim star in the night sky suddenly becoming as bright as the full moon, a transformation so radical it defies belief. This was not a radio burst, it was a full-spectrum eruption in the highest energy light, a scream of radiation that saturated detectors. Astronomers now believe these anomalous X-ray pulsars are simply magnetars wearing a different mask, their defining feature being these rare, gigantic outbursts. The cause is a catastrophic starquake, a magnetic apocalypse. The neutron star's crust, under unbearable stress from twisted internal magnetic fields, finally fractures. But this is not a small crack. This is a global rearrangement, a shattering of the entire magnetic skeleton of the star. As the magnetic field lines snap and violently reconnect into a new, lower energy configuration, they release a torrent of energy that heats the star's surface to hundreds of millions of degrees, flooding space with X-rays. Visually, you would see the entire surface of the city-sized star ignite in a flash of searing light, a brief, artificial sun born from magnetic trauma. The real puzzle is what happens next and before. After the outburst fades, the star returns not to darkness, but to that same quiet, persistent X-ray glow. This quiescent emission is the deeper mystery. With no companion to steal from and a slow spin that cannot power it, the only engine left is the magnetic field itself, slowly decaying and radiating away its energy as heat and X-rays over millennia. An anomalous X-ray pulsar in outburst is a star having a seizure, but in its quiet state, it is a star slowly bleeding magnetic energy, a cooling ember from a fire that burned without flame. These objects show us the two faces of a magnetar, the long, patient decline and the sudden, violent correction, a reminder that the most stable-looking points of light can harbor the potential for instantaneous catastrophe. A star's magnetic seizure is a solitary event, but when neutron stars pair up, they create a laboratory of unimaginable precision. Our 13th unexplained signal comes from a binary pulsar whose heartbeat refuses to obey the simple rules of orbital motion. In these rare systems, a pulsar orbits another dense object, often another neutron star or a white dwarf. By measuring the exact arrival time of each radio pulse over years, astronomers can map the orbit with breathtaking accuracy, detecting shifts smaller than a millisecond. This pulsar timing is so sensitive it can feel the gravitational pull of a planet millions of times smaller than the star itself. Yet in some of these cosmic duets, the pulse arrival times show tiny, persistent anomalies. The rhythm arrives a fraction of a second early or late, in a pattern that cannot be explained by the simple two-body dance of the stars. These timing glitches are clues written in gravity's own language. One compelling explanation hides in the darkness between the two known stars. Could a third body, an unseen planet or a failed star known as a brown dwarf, be orbiting the pair? Its gentle but persistent gravitational tugs would subtly pull the pulsar back and forth, adding a complex wobble to its orbit and delaying or advancing its pulses in a predictable cycle. Visually, you would see the two bright stars circling each other, while a dark, massive shadow circles them both, its presence revealed only by the flawless clock it disturbs. But there is an even more exotic possibility rooted in Einstein's theory of general relativity. The companion star, simply by virtue of its mass and spin, warps the fabric of space-time around it. As the pulsar moves through this warped space, its signals are literally dragged along, an effect called frame dragging. Our current models account for this, but what if the companion is stranger than we think? What if it is a rapidly spinning, ultra-dense object whose frame-dragging effect is more powerful than our equations predict? The tiny timing residuals could be the first hint of relativistic physics we have not yet fully mastered, a whisper that our understanding of gravity, even in its most tested form, might still be missing a piece. These binary pulsars are the ultimate proving grounds for the laws of the universe. Each anomalous pulse is a question posed directly to Einstein's legacy, asking if we need to invite a hidden world into the system or rewrite the rules of the dance itself. The cosmos builds its most precise clocks only to subtly break them, ensuring we never stop listening to the deeper truths ticking beneath the noise. A clockwork anomaly in a distant binary is one thing, but a cosmic shout from our own galactic neighborhood is another. The 14th unexplained signal finally brought the mystery of fast radio bursts home. In April 2020, multiple telescopes, including the Canadian CHIME Array and a survey in the United States called STARE-2, caught a brilliant flash of radio waves. It lasted only a millisecond, but it packed a staggering punch. The source was not in a distant galaxy billions of light-years away. It was inside our own Milky Way, a mere 30,000 light-years from Earth. And it came from a known object, the magnetar SGR 1935 plus 2154, the very star we have seen erupt before. This was the Rosetta Stone moment astronomers had been waiting for. For the first time, a fast radio burst was definitively linked to a specific, identified cosmic object. The signal itself was a fascinating hybrid. It was incredibly bright, but compared to the most powerful extragalactic bursts that travel across the universe, it was actually somewhat subdued. Think of it this way: if the extragalactic FRBs are sonic booms heard from across an ocean, this galactic burst was the same kind of crack heard from just down the street. The reduced volume made perfect sense. It had a much shorter journey through space, losing less energy along the way. This direct comparison proved that the mind-bending energy calculated for distant bursts was real, not an error in our measurements. The detection was a monumental confirmation. Magnetars, with their apocalyptic magnetic fields, are indeed factories for at least some of these bizarre signals. The Starquake model gained immense credibility. A crustal snap on this city-sized star could unleash a directed beam of radio energy powerful enough to be seen across intergalactic distances if the magnetar were far enough away. But this discovery solved one mystery only to deepen another. If magnetars in our galaxy can produce FRBs, does that mean every single fast radio burst out there comes from a magnetar? The answer is probably not. The sheer variety of FRB behaviors, from one-off blasts to precise repeaters, suggests multiple pathways to catastrophe. Our galactic magnetar burst was a singular event from that star, not a repeater like the famous FRB 121102. This implies the universe might have more than one recipe for cooking up a millisecond radio scream. Some could be from young, hyperactive magnetars in stellar nurseries. Others might come from the final, fatal merger of two neutron stars. There could even be sources we have not yet dreamed of. The galactic FRB was a gift, a nearby example we can study in detail, but it also served a warning. The cosmos rarely offers a single, simple answer. By placing a pin in the map of our own galaxy, this signal told us we are living in a laboratory of extreme physics, and that the most exotic signals in the universe are not just out there, they are happening right here at home. Even from 50,000 light-years away, a single star can reach out and touch our world. This is our 15th unexplained signal, the Christmas burst. On December 27, 2004, satellites designed to monitor nuclear detonations on Earth suddenly screamed in alarm. Their sensors were not picking up a weapon but a cosmic cataclysm. A magnetar named SGR 1806-20 had unleashed a giant flare, a burst of gamma rays so intense that for a fraction of a second, it outshone the full moon, becoming the brightest extrasolar object ever recorded in human history. The energy released in that 20th of a second was greater than what our sun will emit over the next 250,000 years. But the true measure of its power was not just seen, it was felt. The gamma-ray pulse traveled for millennia across space, and when it finally arrived, it slammed into the upper layers of Earth's atmosphere. The intense radiation ionized atoms, creating a sudden, detectable disturbance in the ionosphere that rippled around the planet. For a moment, our world's protective electromagnetic skin vibrated to the tune of a star's death cry. The cause of this apocalyptic event was a starquake of unimaginable scale. This was no mere crustal crack. The magnetar's internal magnetic field, twisted beyond endurance, underwent a catastrophic global rearrangement. Think of the entire magnetic skeleton of the star, a complex web of unimaginable force, suddenly snapping and re-knitting itself into a simpler, more stable shape. This violent release of pent-up magnetic energy heated the star's surface to hundreds of billions of degrees, bathing everything around it in a lethal bath of gamma rays and high-energy particles. Had this magnetar been closer, the consequences would be the stuff of science fiction horror. If a giant flare like this occurred within 10 light-years of Earth, the gamma-ray blast would strip away our planet's protective ozone layer within months. The sky would turn into a conduit for deadly ultraviolet radiation from our own sun, triggering a mass extinction event on the ground. Any hypothetical planet orbiting the magnetar itself, even at a great distance, would be periodically sterilized, its atmosphere scoured away and its surface bathed in radioactive fire. The Christmas burst was a stark demonstration of our cosmic good fortune. We witnessed the full, terrifying majesty of a magnetar's fury from a safe distance, a front-row seat to an explosion that, in a different stellar neighborhood, would spell doom. It serves as a sobering reminder that the universe is not just mysterious. It is also profoundly dangerous, capable of reaching across the void with a hand that can both illuminate the sky and erase worlds. A star's final cry can etch its story across space for millennia, but sometimes the story we read makes no sense. Our 16th unexplained signal is a cosmic mismatch, a pulsar that appears far older than the glowing tomb it rests within. Take pulsar J0538 plus 2817, a neutron star spinning about 7 times per second, nestled inside the supernova remnant S147. To understand the paradox, you need to know how astronomers date these objects. A pulsar's age is estimated by its spin-down rate, how quickly its rotation is slowing. It is like a spinning top. A fresh one spins fast and slows rapidly, while an old, tired one spins slowly and loses speed more gradually. By measuring this slowdown, you get a characteristic age, a rough estimate of how long it has been ticking. The remnant's age, however, is measured by its expansion. When a star explodes, it blasts a shell of glowing gas outward at thousands of kilometers per second. By measuring how far that shell has expanded and how fast it is moving, you can calculate how long ago the explosion happened. These two clocks should tell the same time. They rarely match perfectly, but for this pulsar, the discrepancy is staggering. The supernova remnant appears to be only about 30,000 years old, a cosmic infant. The pulsar's spin-down age, however, suggests it is a venerable 600,000 years old. That is a difference of over 500,000 years. It is as if you found a medieval knight's suit of armor buried inside the ruins of a building constructed last week. How can a pulsar be 20 times older than the explosion that supposedly created it? One possibility is that the pulsar was born a zombie, spinning unusually slowly from the moment it emerged. Most neutron stars are born spinning furiously, dozens of times per second, a consequence of the collapsing core conserving its angular momentum. But if this star's progenitor was a slow rotator, or if the explosion was unusually messy, the newborn pulsar might have started its life with a languid spin. Its characteristic age would then be a massive overestimate because the formula assumes it was born spinning fast. The other possibility is that we are misreading the tombstone. The supernova remnant's expansion might have been slowed by running into denser interstellar material, making it look younger and more compact than it truly is. Or perhaps the pulsar received an enormous kick from its asymmetrical birth explosion. Visualize the supernova blast not as a perfect sphere, but as a lopsided detonation. The neutron star could have been shot out like a cannonball, traveling for hundreds of thousands of years before finally entering the gaseous shell we see today. In this scenario, the pulsar is not a resident of this remnant. It is merely a visitor passing through, a wanderer that has finally caught up with the slower moving debris from its own ancient birth. This cosmic mismatch forces us to question the simple stories we tell about stellar death. It suggests that the moment a neutron star is born can be far more complex and violent than we thought, capable of producing slow-spinning anomalies or imparting kicks so powerful a star can outrun its own past. A pulsar can outrun its own past, but some choose a far more sinister path, staying close to slowly consume their partner. Our 17th unexplained signal comes from a cosmic vampire, the Black Widow pulsar. This is a millisecond pulsar, spinning hundreds of times per second, but it is not alone. It is locked in a lethally tight orbit with a small, low-mass star, a companion so close the entire system could fit inside our sun. The pulsar's intense radiation and relentless wind of high-energy particles are quite literally cooking and stripping away its partner, blowing a cloud of vaporized stellar material into space. This creates a bizarre and variable celestial fog, and as this fog passes between the pulsar and Earth, something strange happens to the signal. The pulsar's normally crisp radio pulses do not simply cut off, they smear, distort, and fade in ways that change from orbit to orbit. These are not clean eclipses, they are messy, dynamic absorptions. By studying exactly how the radio waves are scattered and delayed as they pass through this ablated cloud, astronomers can essentially perform a cosmic ultrasound, mapping the density, turbulence, and structure of this stellar plasma in real time. One orbit might show a sharp dip, suggesting a dense clump of material. The next might reveal a gradual smearing, indicating a more diffuse, wispy tail. The Black Widow is more than just a destroyer, it is a natural particle accelerator of phenomenal power. The interaction between the pulsar's wind and the companion's atmosphere creates shocks where particles are boosted to near-light speeds, potentially generating unusual flashes of gamma rays or X-rays that vary with the orbital dance. Visually, an artist's impression would show a brilliant, spinning pulsar, its twin beams of radiation slicing through space, while a stream of glowing gas is torn from the ravaged surface of its orange dwarf companion, forming a swirling, turbulent cloud that periodically engulfs the entire system. This is a relationship of cosmic horror and profound utility, a laboratory where we can watch a star being disassembled and use its death throes to probe the physics of plasmas and particle acceleration in a way no experiment on Earth ever could. The signal's variations are a direct transmission from the front lines of stellar destruction, a whisper from the cloud that is both a tomb and a telescope. The Black Widow's deadly embrace is a constant, predictable horror, but some neutron stars refuse to follow any schedule at all. Our 18th unexplained signal introduces the cosmic misfits known as rotating radio transients, or ARAT. These are the ghosts of the pulsar world. Instead of a steady, metronomic beat, ARAT will suddenly spit out a single, incredibly bright radio pulse and then fall silent. That silence might last for minutes, hours, or even days before another solitary burst erupts from the void with no discernible pattern to the chaos. Discovering these objects is like trying to find a specific firefly in a vast, dark field that only flashes once every few hours. You must stare at the same patch of sky for an impossibly long time, waiting for that one brilliant moment, and even then you might miss it. This makes ARAT among the hardest neutron stars to find and catalogue. So what could cause such erratic behavior? One leading theory is that we are looking at the final, sputtering breaths of ancient pulsars. Imagine a lighthouse whose mighty rotating beam has almost run out of power. Its light, once steady and brilliant, now flickers unpredictably. The neutron star's magnetic field, the engine for its radio emission, may have decayed to such a weak state that it can only occasionally accelerate enough particles to create a burst we can detect. It is a star on the verge of radio silence, its voice reduced to random, dying gasps. Another possibility is a trick of geometry. All pulsars beam their radiation from magnetic poles, and we only see them if that beam sweeps across Earth. ARAT could be a perfectly ordinary pulsar, but one whose beam is so narrow or pointed at such an oblique angle that it only flashes across our line of sight for a single rotation every few hundred or thousand spins. It would be a lighthouse with a tightly focused beam on a wildly wobbling platform, its light only rarely piercing our particular window on the shore. This connects them to other transient mysteries. Could some of the one-off fast radio bursts simply be extragalactic RAT, a single ultra-bright pulse from a dying or misaligned neutron star in a distant galaxy? The discovery of RAT forced astronomers to realize that the neutron star population is far more diverse than the steady tickers we first found. They represent the outliers, the faint whispers and erratic shouters that had been hiding in the gaps between the regular pulses all along. They remind us that for every cosmic clock we hear ticking, there may be a dozen more whose timepieces we cannot read, their stories told in sporadic, brilliant fragments. Erratic radio whispers hint at a star's final days, but to truly measure a neutron star's power, we must listen to a different kind of scream. Our 19th unexplained signal is written not in radio waves, but in the language of X-rays, a phenomenon known as the cyclotron line. This is one of the most precise measurements in all of astrophysics, and its elusive behavior is a puzzle of pure physics. When gas from a companion star spirals onto a neutron star's magnetic poles, it is heated to millions of degrees, emitting a torrent of X-rays. But the star's magnetic field, trillions of times stronger than Earth's, acts as a cosmic filter. Within the searing column of infalling matter, electrons are forced to spiral along the magnetic field lines. These gyrating electrons can absorb X-rays at one very specific energy, a frequency dictated solely by the strength of the magnetic field itself. It is like a tuning fork for the universe's most powerful magnets. When astronomers spread the X-ray light into a spectrum, this absorption shows up as a sharp dip, a dark line on a bright graph. The position of that line gives a direct, unambiguous reading of the magnetic field strength, no estimates or models required. Yet this cosmic fingerprint is maddeningly inconsistent. In observations of the same neutron star, sometimes the cyclotron line appears sharp and clear, a definitive notch in the data. Other times it vanishes completely, as if the star's magnetic field has simply switched off. The line can even appear to split into two or shift to a slightly different energy. This is not an instrument error, it is a real change in the star's screaming voice. The explanation lies in the brutal, dynamic geometry of the accretion column itself. Imagine that column not as a smooth pillar of light, but as a turbulent, superheated tornado. Its shape, density, and temperature are in constant flux. If we are viewing the column directly from the side, our line of sight passes through a great deal of this spiraling plasma, giving the electrons plenty of opportunity to absorb their characteristic X-rays, and the line appears strong. But if we are looking almost directly down the magnetic pole, staring into the eye of the storm, our view is different. We see the hottest, deepest part of the column where the X-rays are created, but we pass through less of the surrounding cooler plasma where the absorption happens. The line grows faint or disappears entirely. Furthermore, the magnetic field is not a simple bar magnet, it is twisted and complex. Different heights in the column might have slightly different field strengths, which could cause a single line to blur, split, or shift as conditions change. The graph of these appearing and disappearing lines is a live readout of a cosmic maelstrom, a direct window into the chaotic physics at the surface of a star where gravity and magnetism meet in a storm of radiation. It tells us that even a fundamental property like magnetic field strength is not a static number etched in stone, but a living, breathing force, its voice changing with the star's turbulent weather. A star's magnetic fingerprint can flicker, but its very spin can stumble with a mystery all its own. Our 20th unexplained signal is a glitching magnetar with a delayed reaction. Magnetar SGR 1935 plus 2154, our frequent and violent protagonist, experienced a significant glitch, a sudden increase in its spin. This in itself was not unusual, but the star's radiative properties, the way it emitted X-rays, did not change at that moment. Instead, they shifted only weeks or months later, as if the star's surface needed time to process the trauma that had already reshaped its core. In a typical glitch, the star's spin and its outward flash of radiation change in lockstep, a coordinated event. This delay was a profound clue that something different was happening deep within the star's structure. To understand this, we must journey inside the neutron star. Picture it in layers. The outermost layer is a rigid crust of atomic nuclei, a solid shell a kilometer thick. Beneath that lies a sea of superfluid neutrons, a quantum liquid that flows without any friction. The glitch itself is thought to occur when billions of microscopic vortices in this superfluid suddenly unpin from the solid crust above, transferring a massive jolt of rotational energy upward in an instant, spinning the crust faster. This is the immediate spin-up, but the star's magnetic field, which generates the X-rays we see, is anchored in both the superfluid interior and the solid crust. The theory suggests the glitch sent a slow wave of change propagating through the star's complex interior. Imagine dropping a heavy stone into a vat of thick, strange honey. The initial splash is immediate, but the ripples take a long time to reach the edges and change the shape of the surface. In the magnetar, the sudden unpinning event might have triggered a gradual reorganization of the internal magnetic field, a slow rewiring that only manifested in the star's external X-ray emission after it finally reached the surface weeks later. Alternatively, the solid crust itself may have undergone a slow, plastic healing process. After the violent starquake that likely triggered the glitch, the crust did not simply crack and settle. It may have continued to deform and flow over time, like glacial ice under immense pressure, gradually shifting the anchor points of the magnetic field lines until the outside world could see the difference. This delayed reaction is a direct observation of the deep, sluggish connection between a neutron star's hidden engine and its visible face. It tells us these objects are not simple, solid spheres, but intricate, layered entities where a shock in the quantum heart can take a month to whisper its arrival to the universe. The star's surface, it seems, is the last to know its own secrets. A star's delayed reaction reveals its deep inner life, but sometimes a neutron star chooses to speak in a voice we are completely deaf to. This is our 21st unexplained signal, the silent gamma-ray pulsar. NASA Fermi Gamma-Ray Space Telescope has been mapping the high-energy sky for over a decade, and in its data, astronomers have found something that defies the classic image of a pulsar. These objects spin with perfect regularity, their gamma-ray pulses arriving like clockwork, yet when radio telescopes are pointed at their precise coordinates, they hear nothing. Absolute silence. These are lighthouses that shine only in the most energetic light, their radio beacons either switched off or pointed elsewhere. The mystery cuts to the core of how neutron stars work. For decades, the model was straightforward. A pulsar's spin and magnetic field accelerate charged particles near its poles, creating beams of radiation that sweep through space. We assumed these beams were broad, or at least that radio and gamma rays were produced in tandem. The silent pulsars prove that assumption is wrong. One explanation is a matter of geometry and focus. The radio beam could be incredibly narrow, a tight laser pointer compared to the wide floodlight of gamma rays. If that narrow radio beam never sweeps across Earth, we would never hear it, even as the star's powerful gamma-ray pulse washes over us with every rotation. We are witnessing a cosmic lighthouse from an angle where we see its powerful searchlight, but miss its accompanying foghorn entirely. The other possibility is more fundamental. The radio emission mechanism itself might be suppressed in these extreme environments. The process that creates coherent, bright radio waves requires specific conditions in the pulsar's magnetosphere, a precise dance of particles and magnetic fields. In some neutron stars, the magnetic field might be too strong, too weak, or configured in such a way that this dance never begins. Instead, all the star's rotational energy is channeled directly into creating gamma rays through different, more efficient processes, like the curvature radiation from particles following the extreme magnetic field lines. The radio engine, in essence, never turns on. This discovery forces a major revision of our celestial senses. If a significant fraction of neutron stars are radio quiet, it means our traditional surveys, which rely on radio telescopes, have been missing an entire population. The gamma-ray sky is revealing the silent majority. The implications are staggering. There could be thousands, even tens of thousands, of these powerful but voiceless stellar corpses in our galaxy alone, spinning in the dark, their presence known only by the periodic flash of their invisible, deadly light. They are ghosts made real only by the most penetrating eyes we have, a reminder that what we do not hear can be just as important as what we do. A silent gamma-ray pulsar is a ghost we can only see, but what about a cataclysm we could both hear and feel? The neutron star merger known as GW 170817 was a triumph of multi-messenger astronomy, a cosmic event detected in both gravitational waves and light. Yet in its complex aftermath, a potential 20-second unexplained signal may have whispered from the wreckage. After the initial gravitational wave chirp and the brilliant kilonova glow faded, astronomers kept watching. They monitored the merger site with radio and X-ray telescopes for months, expecting the signal to decay as the expanding debris cooled. While the observations largely matched predictions for a structured jet of material punching through the merger debris, there were intriguing subtleties in the late-time data. The radio emission faded, but not quite as smoothly as some models projected. The X-ray light curve, a graph of its brightness over time, showed a slight plateau or excess that some researchers argued was statistically significant. These faint anomalies are the echoes in question. Could they be the signature of something surviving, however briefly, in the heart of the collision? One electrifying theory is that the two neutron stars did not immediately form a black hole. Instead, they may have merged into a hypermassive neutron star, a single, rapidly spinning, and intensely magnetized object that lived for mere seconds or minutes before its own weight crushed it into a black hole. This fleeting magnetar remnant would have possessed a magnetic field 1,000 trillion times Earth's strength and spun nearly 1,000 times per second. In its brief, violent life, it would have pumped enormous energy into the surrounding ejector, like a blender stirring the aftermath of the explosion. This injected energy could have caused the observed X-ray plateau and altered the radio fade, creating a subtle bump on the light curve, the dying pulse of a monster that existed for only a heartbeat. Another possibility lies in the geometry of the jet itself. The jet that created the visible afterglow was likely narrow and powerful, like a cosmic blowtorch. If this jet was not perfectly smooth, but instead had internal structure or clumps, or if it interacted with a torus of debris swirling around the new black hole, it could produce a more complex fading pattern with small rebrightenings or slower declines in certain wavelengths. Visually, simulations show the merger as two ultra-dense spheres spiraling inward in a final, fatal dance, resulting in a blinding flash and an expanding cloud of neutron-rich material glowing with the light of newly forged gold and platinum. In one scenario, a brilliant, spinning magnetar sits at the center, its magnetic fields lashing the cloud before it winks out. In another, a narrow pencil beam of energy drills through the cloud, its turbulent interaction creating faint ripples in the signal we receive. These potential echoes, whether from a dying magnetar or a turbulent jet, are probes of the most extreme states of matter in the universe. They ask what the immediate product of a neutron-star merger truly is, and whether the boundary between the most massive neutron star and the lightest black hole is a sharp cliff or a mysterious temporary shore. The data from GW170817 may hold a faint signature written in that uncertain moment, a final secret from a collision that shook space-time and sprinkled the cosmos with stardust. The echoes of a stellar merger fade into a complex aftermath, but sometimes the most dynamic story is not the star, it is the storm it creates. Our 23rd unexplained signal swirls around the neutron star, a pulsar wind nebula with a mind of its own. The most famous example is the Crab Nebula, the glowing remnant of a supernova witnessed on Earth in 1054. At its heart spins a pulsar 30 times a second, blasting out a fierce wind of charged particles and magnetic fields. This wind inflates a vast, shimmering bubble of radiation around the star, a cosmic accelerator visible from radio waves to gamma rays. For centuries, this nebula was considered a beautiful but relatively stable tomb. Then our most powerful telescopes revealed it was alive. Time-lapse X-ray and gamma-ray observations of the crab's core show a landscape in constant, violent motion. Bright knots and wisps of material race outward at half the speed of light, appearing, shifting, and vanishing over mere days. The entire inner nebula flickers and flares, its high-energy brightness sometimes doubling in a matter of hours. This is not the steady glow of ancient debris. This is a live broadcast from a battlefield where the pulsar's wind meets the slower-moving shell of the supernova remnant. The unexplained variability is a puzzle of power and turbulence. The pulsar wind is not a gentle breeze. It is a supersonic gale of electrons and positrons, carrying the star's rotational energy into space. When this wind slams into the nebula's outer boundaries, it creates a massive shock wave, a standing wall of energy where particles are whipped to near light speeds and emit the brilliant X-rays we see. The moving knots are likely ripples or blobs in this shock front, massive structures larger than our solar system dancing in real time, but the sudden flares are the deeper mystery. They suggest episodes of catastrophic magnetic reconnection within the nebula itself. Picture the magnetic field lines embedded in the pulsar wind, like strands of spaghetti all flowing outward. These lines can become tangled and stressed. When they suddenly snap and reconnect, they release enormous energy in a localized blast, a magnetic short circuit that lights up a section of the nebula like a flare in a thunderstorm. This process is similar to what causes solar flares on our sun, but here it operates with 1 trillion times more energy and on a vastly larger scale. The nebula, therefore, is not just a passive cloud. It is an active, turbulent engine, a natural particle collider where the raw power of the neutron star is converted into a chaotic light show. Watching its changes is like studying the weather patterns of a hurricane, but a hurricane made of antimatter and magnetic force, where the gusts can move at the speed of light and the lightning outshines stars. The pulsar wind nebula's restless behavior proves that even the graves of stars are not places of quiet, but arenas where physics runs in its most extreme and unforgiving form. One of the most unsettling mysteries is a star that simply goes missing. This is our 24th unexplained signal, the case of the disappearing pulsar. Astronomers have a vast catalogue of these cosmic clocks, each with its own unique fingerprint of spin and position. Occasionally, when they revisit an old entry for follow-up study, they point their telescopes at the precise coordinates, tuned to the exact frequency, and hear nothing. The steady tick is gone. The star has vanished from the radio sky. It is a cosmic ghost, a beacon that was there one day and absent the next. The immediate assumption is not that the star itself has evaporated. A neutron star is nearly indestructible. Instead, the silence points to a profound change in the signal we rely on to see it. One dramatic possibility is a glitch of unprecedented magnitude. We have seen how a starquake can cause a sudden spin-up, but what if the event was so catastrophic it did not just speed the star up, It completely altered its fundamental rotation period. Imagine a pulsar spinning 10 times a second. A monstrous internal rearrangement, a true stellar seizure, could theoretically change that period to 5 seconds or 50 seconds. To our automated surveys searching for the old rhythm, it would be invisible, a known voice suddenly speaking in an unrecognizable language. Another explanation is a grand and final precession. The star's magnetic axis, the source of its beam, might be slowly wobbling over centuries. The initial detection was a moment of perfect alignment, a brief window where its lighthouse beam swept directly over Earth. Now that slow cosmic wobble has carried the beam away, perhaps for thousands of years. We caught it in a fleeting moment of visibility, and now it shines for other parts of the galaxy, its radio voice lost to us. There is also the haunting precedent of the switching pulsar. Could this missing star be in an extremely long off phase of its cycle, a radio silence that lasts for decades or even centuries? Our observations would then be a matter of tragic timing, a snapshot of a star in its quietest mood, mistaken for its permanent state. Then, of course, there is the humbling possibility of a cosmic mirage. The initial detection itself might have been an artifact, a rare and perfect storm of terrestrial interference, or a transient burst from another object that mimicked a steady pulse just long enough to be catalogued. It was never a pulsar at all, just a ghost in the machine. The frustration for astronomers is palpable. It is like having a wanted poster for a cosmic fugitive with a known alias and last known location, but every time they stake out the spot, the suspect is gone. Each missing pulsar represents a story interrupted, a data point that refuses to be pinned down. It forces a question that challenges our sense of cosmic order. How many of the steady beacons we think are permanent are actually just temporary visitors in our field of view, winking in and out of perception on timescales we are only beginning to fathom? The silence where a pulse should be is its own kind of signal, a reminder that the universe's ledger is written in pencil, not ink. The final signal on our list is the cosmic trickster, the one that was not a neutron star at all. It began with all the hallmarks of a stellar corpse, a steady, repeating radio pulse that seemed to point to a spinning magnetar in a distant galaxy. Astronomers catalogued it, theories were drafted, and for a time it took its place among the other unexplained signals. But something felt off. The signal's environment was too bright, its location too energetic for a lone, city-sized object. The breakthrough came not from a radio telescope, but from an X-ray observatory. When scientists trained those eyes on the same coordinates, they saw not the faint glow of a neutron star, but the searing, brilliant heart of an active galactic nucleus, a supermassive black hole millions of times the mass of our Sun, feasting on gas at the center of its galaxy. The radio pulses were not the spin of a stellar corpse, but likely colossal jets of material blasting from the black hole's poles, their flickering masquerading as a pulsar's beat. This was the great cosmic mimic. Visually, the comparison is stark. On one side, a neutron star is a tiny, dense point, its influence extending only a few thousand kilometers. On the other, an active galactic nucleus is an engine that can outshine its entire host galaxy, a vortex of light and matter on a scale of light years. One could fit inside a small city, the other could swallow our solar system without a trace. Yet from billions of light years away, their voices in one narrow band of light could sound confusingly similar. This misidentification is not a failure, it is a masterclass in how astrophysics truly works. It underscores the absolute necessity of multi-wavelength observations. The universe speaks in every frequency, from radio waves to gamma rays, and listening with only one ear guarantees you will misunderstand the conversation. A signal is just a data point, a clue. Its true meaning only emerges when we bring every tool we have to bear, cross-checking the radio chirp against the X-ray blaze and the optical glow. The process is one of relentless elimination and humility. Each dead end, each corrected hypothesis teaches us more about the complexity of the cosmos than a dozen easy answers ever could. It reminds us that the universe is a place of infinite variety, where black holes can impersonate neutron stars, and where the most important skill is not just hearing a signal, but knowing how to listen to everything else around it. The final lesson of these 25 mysteries is that the map of the unknown is always being redrawn, not just by what we find, but by what we thought we knew that turns out to be something else entirely. From cosmic mimics to vanishing stars, these 25 signals paint a portrait of a universe that is far stranger, far more dynamic than we ever dreamed. We have listened to stars that repeat, stars that stumble, and stars that simply switch off. We have witnessed magnetic fields so powerful they can crack a planet-sized object and gravitational waves that sing of ancient collisions. Each one of these anomalies, from the first Lorimer burst to the last mistaken identity, is a testament to the extreme physics at the edge of reality. They exist where matter is crushed to its absolute limit, where gravity bends light into knots, and where magnetism becomes a tangible, destructive force. These are not mere curiosities, they are fundamental probes into the laws that govern everything. Every unexplained signal is a clue waiting on a detective's desk. That faint timing residual in a binary pulsar could reveal a hidden planet or a flaw in Einstein's gravity. The slow dimming of a once bright beacon might map the final death rattle of a magnetic field. The next great discovery in physics may not come from a particle accelerator underground, but from a flicker of radio waves that traveled across the galaxy for millennia. This is why we build bigger telescopes and sharper detectors to listen more closely to these cosmic whispers. The answers are out there, encoded in the static between the stars. So the next time you look up at the night sky, remember that it is not a silent, static painting. It is a symphony of invisible forces and screaming stellar corpses, a conversation in a language we are only beginning to learn. Your curiosity is part of that journey. Which of these 25 mysteries baffles you the most? Let us know in the comments below. And if you want to join us as we decode the next great signal from the cosmos, be sure to subscribe. The universe is still talking. Let's keep listening.